The vast expanse of our solar system stretches far beyond what we can see with the naked eye. While the planets and their moons have been subjects of exploration for decades, the true frontier lies in the distant and enigmatic outer edges. Beyond Neptune, in the frozen darkness, lies the Kuiper Belt, a region filled with icy remnants from the early solar system. Further still, at the very boundary of our sun's influence, is the Heliopause, marking the transition into interstellar space. And even beyond that, in the theoretical depths of cosmic distance, lies the mysterious Oort Cloud, a vast shell of icy bodies that may hold the secrets to the origin of long-period comets. A journey to the edge of the solar system is one of the most ambitious endeavors humanity could undertake. It is not merely a test of our technological capabilities, but a quest for knowledge, seeking to uncover the nature of our cosmic neighborhood. What lies beyond the comforting warmth of our sun? How does the influence of our star wane as we drift further into the unknown? These questions drive scientists to propose missions that will take us beyond the planets and into the realm of deep space. Such a mission would require unprecedented engineering feats. Traditional chemical propulsion would be insufficient for a voyage spanning billions of kilometers. Instead, advanced propulsion systems such as nuclear electric propulsion, ion drives, or even experimental solar sails could be necessary. Communication with a probe at such extreme distances would be another challenge, as signals from the edge of the solar system take hours, if not days, to reach Earth. Meanwhile, the harsh environment of deep space, with its cosmic radiation and near absolute zero temperatures, poses additional obstacles that engineers and scientists must overcome. Yet, despite these challenges, the rewards are immense. A spacecraft venturing into the farthest reaches of our solar system could provide invaluable insights into the nature of the heliosphere, the protective bubble created by the sun's solar wind. It could study the Kuiper Belt's icy worlds, revealing clues about the formation of our planetary system. Perhaps most intriguingly, it could be our first step toward truly interstellar exploration, paving the way for humanity's future among the stars. In the chapters ahead, we will explore the intricacies of such a journey, delving into the science, technology, and vision required to reach the outermost edges of our solar system. This is not just a hypothetical exercise, it is the foundation for the next great leap in space exploration. Let us embark on this grand odyssey and imagine what it would take to send a probe beyond the last light of our sun and into the cosmic abyss. To embark on a journey of such unprecedented scale, meticulous preparation is essential. This mission will push the boundaries of human ingenuity, demanding cutting-edge technology, sustainable energy solutions, and robust communication strategies. Every aspect of this expedition, from the design of the spacecraft to the propulsion methods that will carry it across billions of kilometers, must be optimized for efficiency, durability, and adaptability in the harsh environment of deep space. The vast distances involved in this mission necessitate propulsion systems far more advanced than conventional chemical rockets. Ion propulsion, which has already been tested on missions such as NASA's Dawn spacecraft, offers an efficient means of acceleration by expelling ions at high velocities. Nuclear electric propulsion, leveraging nuclear fission to generate power for ion thrusters, could provide the sustained acceleration necessary for reaching the solar system's outer boundaries. Meanwhile, solar sails, using the momentum of photons from the sun, could provide a long-duration thrust that continues to push the spacecraft outward even in the absence of fuel. As the probe ventures beyond the orbit of Jupiter, solar energy becomes less viable due to the diminishing intensity of sunlight. Radioisotope thermoelectric generators, RTGs, which convert heat from radioactive decay into electricity, have long been the standard for deep space missions such as Voyager and New Horizons. However, next-generation nuclear reactors may offer more efficient and long-lasting power solutions, ensuring continuous operation of scientific instruments and communication systems for decades. Maintaining contact with a spacecraft at such extreme distances is a formidable challenge. As the probe moves further from Earth, signal delays increase dramatically, requiring advanced data compression and long-range transmission methods. High-gain antennas, capable of focusing signals with extreme precision, will be essential. Additionally, optical communication using laser beams could provide a higher data rate compared to traditional radio waves, ensuring that valuable scientific data is transmitted back to Earth with minimal loss. The complexities of deep space travel require a harmonious integration of these technologies. Engineers and scientists must not only design a spacecraft that can survive for decades in the void, but also anticipate the unpredictable conditions of interstellar space. With the right innovations and a commitment to exploration, humanity can push beyond its planetary cradle and take its first steps toward the infinite unknown. With the spacecraft now constructed and every system tested, the time has come for departure. This phase of the mission involves an intricate dance with gravity, a precise trajectory, and a journey through some of the most awe-inspiring regions of our solar system. From launch to the Kuiper Belt, the Voyage is a testament to our ability to navigate the vast cosmic distances that separate us from the frontier. The journey begins with a powerful launch from Earth's surface, likely utilizing a heavy-lift rocket such as NASA's Space Launch System, SLS, or SpaceX's Starship. After escaping Earth's gravity, the spacecraft will undergo trajectory adjustments to align with the most efficient path outward. Gravity assists, maneuvers that use the gravitational pull of planets, will be crucial in conserving fuel and accelerating the spacecraft toward the outer solar system. Beyond Mars, the probe will encounter the asteroid belt, a region filled with rocky remnants of the early solar system. While most asteroids are spread out, careful navigation is necessary. Next comes Jupiter, the gas giant whose immense gravity can provide a critical slingshot boost, propelling the spacecraft at even greater speeds. Beyond Jupiter, the spacecraft enters the realm of the outer planets. Saturn, with its mesmerizing rings, presents a breathtaking sight. Its massive magnetic field and dynamic atmosphere, rich in hydrogen and helium, are key subjects of study. The probe may pass near Titan, Saturn's largest moon, with its dense nitrogen atmosphere and liquid methane lakes, one of the most Earth-like environments in the solar system. Further along, Uranus appears as a pale blue sphere, tilted on its side due to a cataclysmic impact billions of years ago. The spacecraft's instruments could study the planet's faint rings and unique magnetic field, which wobbles irregularly. Beyond Uranus, Neptune emerges with its deep azure hue and the violent storms of its atmosphere. The spacecraft might pass close to Triton, Neptune's largest moon, which orbits in retrograde motion, and may be a captured Kuiper Belt object. As the probe leaves Neptune behind, it enters the Kuiper Belt, a vast region filled with frozen relics from the solar system's formation. Here, it encounters Pluto, once considered the 9th planet, and its companion, Charon. The spacecraft could conduct high-resolution imaging and spectral analysis of these distant worlds, revealing new insights into their geology, surface compositions, and potential subsurface oceans. Beyond Pluto, the probe continues its journey through a swarm of icy bodies, some potentially harboring organic materials that may provide clues about the origins of the solar system. As the spacecraft leaves the Kuiper Belt behind, it approaches a boundary unlike any other, the edge of the Sun's influence. This is the Heliopause, the outermost region of the heliosphere where the solar wind slows and meets the interstellar medium. It is a place of profound significance, marking the true transition from our solar system into interstellar space. The heliosphere is a protective bubble created by the solar wind, a constant stream of charged particles emitted by the sun. As the spacecraft moves outward, the density of these particles decreases, and the solar wind slows to a near halt. The heliopause is the final boundary where the solar wind is stopped entirely by the pressure of the interstellar medium, cosmic radiation and gas from the galaxy itself. Beyond the heliopause, the environment changes dramatically. The spacecraft will be exposed to high-energy cosmic rays from the wider galaxy, which are normally deflected by the sun's magnetic field. These particles can provide valuable data on the nature of interstellar space and the structure of the heliosphere, helping us understand how our solar system interacts with the broader cosmos. Crossing the heliopause is more than just a scientific milestone. It is a historic moment for humanity. Only the Voyager 1 and 2 probes have accomplished this feat so far, providing the first direct measurements of interstellar space. Future missions equipped with more advanced instruments could analyze the composition of interstellar gas, detect distant cosmic waves, and even search for signs of galactic magnetic fields. This transition is the true beginning of interstellar exploration, the first step beyond the confines of our solar system and into the great unknown. Having crossed the heliopause and ventured beyond the Kuiper Belt, our spacecraft now approaches what is perhaps the most mysterious and least understood region of our solar system, the Oort Cloud. This hypothetical shell of icy bodies, stretching potentially up to a light year from the Sun, represents the outermost boundary of our solar system. Unlike the relatively flat disk-like structure of the Kuiper Belt, the Oort Cloud is thought to form a vast spherical shell surrounding the Sun, extending into interstellar space. The Oort Cloud was first hypothesized in 1950 by Dutch astronomer John Oort as an explanation for the origins of long-period comets that take thousands or even millions of years to complete a single orbit around the Sun. Unlike short-period comets from the Kuiper Belt, which are influenced by the gravity of the outer planets, Oort Cloud comets are thought to be remnants of the early solar system, preserved in deep freeze far beyond the planets. Scientists theorize that the Oort Cloud consists of trillions of icy bodies, ranging in size from tiny frozen fragments to objects potentially hundreds of kilometers in diameter. These primordial bodies may contain some of the most pristine material from the birth of our solar system, offering a unique opportunity to study its original composition. While no spacecraft has ever visited the Oort Cloud, indirect evidence for its existence comes from the behavior of long-period comets. These comets appear suddenly in the inner solar system, with highly elongated orbits that suggest they were disturbed from a much more distant, spherical reservoir. Some of the most famous comets, such as a comet Hale-Bopp and comet Hyakutake, are believed to have originated from the Oort Cloud. Their compositions reveal complex organic molecules, water ice, and other volatile compounds, raising intriguing possibilities about the role comets may have played in delivering key ingredients for life to Earth. A dedicated mission to the Oort Cloud would allow scientists to directly sample these ancient materials, offering unparalleled insights into the chemistry and conditions of the early solar system. Such a mission could also help refine our models of how planetary systems evolve over billions of years. Reaching the Oort Cloud presents immense technical challenges. At its inner edge, it may begin around 2,000 astronomical units from the Sun, while its outer edge could extend as far as 100,000 astronomical units, in nearly 1/4 of the way to the nearest star. Given current propulsion technology, a spacecraft traveling at Voyager 1 speed, about 17 kilometers per second, would take thousands of years to reach the heart of the Oort Cloud. However, future breakthroughs in propulsion, such as nuclear fusion drives, antimatter propulsion, or even light sail technology, could dramatically shorten this travel time. Additionally, rather than sending a probe all the way to the Oort Cloud, an alternative approach could involve intercepting and studying inbound Oort Cloud comets as they travel toward the Sun. Despite the challenges, the potential scientific rewards of studying the Oort Cloud are immense. It represents the final frontier of our solar system, the last vestige of our Sun's gravitational influence before interstellar space truly begins. Understanding its composition, structure, and dynamics could unlock critical insights into the history of our own solar system, and the countless others scattered throughout the galaxy. As we venture into this distant and enigmatic realm, we stand on the brink of answering one of the greatest questions of all. What lies beyond the solar system? And what secrets do the ancient frozen bodies of the Oort Cloud hold? The journey to the edge of the solar system is not just a mission of exploration. It is a testament to humanity's relentless curiosity and desire to understand the universe. From the sun's influence in the heliosphere to the distant reaches of the Oort Cloud, each boundary we cross expands our knowledge and deepens our appreciation for the vast cosmic ocean that surrounds us. As technology advances, what once seemed like science fiction is becoming increasingly possible. Future missions to the outer solar system and beyond could uncover secrets about our origins, the potential for life elsewhere, and even the pathways to interstellar travel. In the grand scheme of the universe, our solar system is but a tiny island in an endless sea. Exploring its boundaries is the first step in our greater voyage, to one day set sail among the stars. The edge of the solar system is not an end, but a beginning. What lies beyond remains unknown, but the human spirit thrives on the unknown, ever eager to take the next bold step into the infinite expanse of space.